So in the last couple of recordings, we covered this example here for one-dimension diffusion, convection diffusion problem, and we looked into multiple scheme to simulate the or approximate the convection term. And we did this example for two different levels of velocities. We did that for maybe 0.1, and we did for 2.5 meter per second. We so far covered two different types of schemes, right? The first one was the central differencing scheme, and the second one was the upwind scheme. In the central difference scheme, it's really very accurate when we deal with diffusion problems. So it has high accuracy to simulate diffusion problem. It's worked fine for convection when your Peclet number or cell Peclet number is less than 2. In reality, it's the absolute value of Peclet number less than 2, so which means that Peclet number is somewhere between -2 and 2. Okay? Remember, Peclet number is simply the F over D, so it's rho UA over kappa A over delta, so you end up actually having rho U delta over kappa. So Peclet number is simply the convection to diffusion ratio. So when the Peclet number is getting bigger and bigger, this means that convection is more dominant than diffusion, because convection will be 5, 10, 15 times the diffusion, so the convection becomes dominant. For a small Peclet number, the diffusion contribution has to be considered, and this is where the central finite differencing scheme is considered. So again, the first scheme that we covered is central differencing scheme. It's great in diffusion problem. It's great in convection when the cell Peclet number is somewhere between -2 and 2. But we realized that when the Peclet number went high, for that high velocity here, Peclet number was 5. This was Peclet number is very small. So when we did solve the example for 0.1 meter per second, we got very, very accurate results compared to the analytical solution. When the Peclet number went to 5, central difference scheme couldn't simulate the convection nicely, and we get the divergent solution, scattering data going up and down all the time. So we will overcome that by applying different scheme, and the one that we use is actually the Upwind scheme. Upwind scheme is great for convection when the Peclet number is getting bigger than 2. No limits for that. No one mentioned the limit, but it works fine when we did the Peclet number for value equal 5. And if you recall the solution from the Upwind scheme, the analytical solution was like this, and the numerical solution was going something like this. And as soon as the solution, actually this was here. As soon as the solution, the analytical solution changing the direction, we realize a little bit of an error happening here. This is phi and this is the x. Let me actually bring the chart that we discussed this example last time here. So again, this is what happened when we use the Upwind with Peclet number is equal 5, right? Peclet number is equal 5, high velocity. We were getting good results here, but as soon as the analytical solution changing direction here, we got that error here. So we need to find a way to fix that error a little bit. This is really more to understand the nature of each one of these schemes. So as we know that central differencing scheme is always assuming linear change of phi. Either we are talking about the diffusion or the convection, right? So we always assume linear change of phi inside the cell or between the cells. While the Upwind scheme assumed constant phi within the cell. If you recall, for the central differencing scheme, if I pick this is these are the cells 1, 2, 3, 4. Let's say this is 5. I will pick a P. I will pick the east one. We pick the west one. Then we assume there is linear change here. This is phi E. This is phi west. This is phi P. And for the convection, we need phi on the east face, and we need phi on the west face. So if we talk about the diffusion in the central differencing scheme, we do d phi by dx, which is the slope, is simply phi E minus phi P divided by delta xe, right? If we are talking about the east one. And phi east is approximated by the average of phi E plus phi P divided by 2. So either you approximate the convection phi value at the face of the cell, or you are getting the gradient of the phi function also at the face of the cell. We are using 2 points, 1, 2, to get that approximation. This is the central differencing scheme. Central differencing scheme. Let's call that the Upwind scheme. But in the case of the Upwind scheme, if I pick P, E, and west, right? And this is the east face, and this is the west face. We said that if the flow is going that direction, the value of phi on that phase is the same value of phi, right? Of the upstream node, so that's phi P, and phi west is going to be the same as phi west. So phi west is equal phi W. So we assume constant value for phi within the cell. Okay, so that's the main difference. And here we are calculating phi east and phi west using single point. Here we are using 2 points. That's why the central differencing scheme is really more accurate than the Upwind scheme. Okay, because you are using 2 data points to calculate your phi, or you're calculating your ingredient. There will be no change for the diffusion term between this scheme and this scheme, but mostly the error is coming in the convection approximation for the phi on the face cells for the convection term. So the convection term here is more accurate than this one. And for a higher Peclet number, it tells that the convection is becoming more dominant, right? So the convection is equal Peclet number times diffusion. So if this is 5, so the convection is 5 times the diffusion. So you have more convection, but you're also approximating the convection with larger error or less accurate, because you are using only 1 data point. And that's explained. The more Peclet number goes higher, the higher the value of Peclet number, the higher the contribution of the convection. The approximation in the Upwind is really showing error, right? Because it's dependent on a single point. And that's explained why we are seeing that error here, especially when the solution changes direction. So we need to find somehow to improve the Upwind so we can minimize the error when we do the approximation, especially when the analytical solution is changing direction. So that's going to be our upcoming task here. So the diffusion convection problem. Say this is phi A and this is phi B, and you have a flow going this way. The analytical solution or the exact solution, this is x equals 0 here. Just let's put all the information, x equal to L, right? And we know how to calculate F, right? It's rho U A. And we know how to calculate D, right? Which is kappa A over delta. And F over D will give me the cell Peclet number. This is how we get it. So the exact solution for this problem, what's the governing equation? The governing equation is kappa dot or nabla dot rho V phi equal to nabla dot kappa nabla phi. This is 1 dimension, steady, and no source convection diffusion problem, right? This is the differential equation here. because we are doing one dimension, I will put this as rho u phi equal kappa dot nabla dot kappa nabla phi. So this is simply partial rho u phi by partial x equal to, if kappa is constant, it's going to be actually kappa d2 phi by dx squared. Since we are dealing with incompressible fluid, I'm going to take actually rho and u are outside, because rho and u is simply giving me f, which is we always assume constant. So rho u d phi by dx equal kappa d2 phi by, this is dx squared. So this is the differential equation that should give me the exact solution. When you solve this equation analytically, you will end up having that exact solution, phi at any location x minus phi at x equals 0, right? Divided by phi at x equal L minus phi at x equals 0. It's equal to E rho u x divided by kappa minus 1 divided by rho, this is E to the exponent of rho ul over kappa minus 1. And we did use the analytical solution before to compare the results for the central differencing scheme example with the analytical solution. This is what's presented in all these curves by the curve here. That's the exact solution that you see here. So we're still trying to understand the exact solution behavior here, okay? I can simply define Peclet number is rho u delta over kappa, right? So rho from this, rho u kappa over kappa is simply Peclet number over delta. I can substitute and replace that term here and replace that term here. So I will have phi at any value of x minus phi at x equals 0 divided by phi at x equal L minus phi at x equals 0 should equal to E to the Peclet number over delta times x minus 1 divided by E Peclet number over delta times L, right? Whereas L is the total length and delta is the unit length here. So now I can get that phi function. This is constant value, so this is going to be phi A. This will be phi B, and this will be phi A as well. So I'm going to end up having the equation phi at any location x minus phi A, which is the boundary value, divided by phi B minus phi A. It's equal to E to the Peclet number over delta times x minus 1 divided by E Peclet number over delta times L minus 1. So now I can get the exact solution as a function of Peclet number, right? So I now can substitute by Peclet number. Delta is going to be a fixed number. You know what's the delta that you picked up. L is going to be the total length. Delta is known. So there is, I can put Peclet number, then I can change the value of x and see how the solution looks like. So if we did some trial to look to that graphical solution or plotting this graphs here. So let's assume that this is the phi axis. This is the x-axis. So this is x equals 0. I'm going to mark here the location of x equal L. Now I have the boundary condition. This is phi A, and this is phi B. And let's start by assuming that Peclet number is equal 0. How the solution looks like when Peclet number looks 0. What do we mean by Peclet number equals 0? Peclet number is simply rho u A, right? So if this is equal 0, area is not going to be ever 0, but rho u will actually equal 0. So Peclet number equals 0 means that rho u is equal 0. It's impossible rho to be 0. So that's telling me that when Peclet is equal 0, no convection. So the dominant heat transfer mechanism is going to be the diffusion one. If I go back to the differential equation here and put rho u equals 0, what I'm going to get? If rho u is equal 0, let me have this in here. If rho u equals 0, I will have 0 d phi by dx equal to kappa d2 phi by dx squared. This is 0, and kappa will go away, so I will end up having 2 d phi by dx squared equals 0. I'm going to integrate, so I will have d phi by dx equals c1. I will have phi equals c1x plus c2. So I'm getting phi as a function of x is linear. So the solution will be linear between the two boundaries here for p equal 0. Peclet number is equal 0. If you increase Peclet number a little bit, you will find that your solution is coming something like that. Let's do that solid line here. Say this is Peclet number equal 0.5, and this is Peclet number equal minus 0.5. You'll get symmetry solution here. So the higher the value of Peclet number, you will get, say, this is Peclet number equal 1, Peclet equal 1, and Peclet equal minus 1 in here. For very large number of Peclet number, the solution will look like this. And for the negative value, solution will look like this. So this is for Peclet much greater than 1. This is for Peclet much less than, actually it's going to be, yeah, much less than minus 1. Okay? So this is the analytical solution. Analytical solution. What we are trying to do is to use one of the schemes, central differencing scheme, Upwind schemes, to match that analytical solution. That's what we're trying to do here, right? So, and you see that you move from Peclet number equal 0, you lose the linearity of the solution. So you may have something looks like this. So still, linear approximation could be working, but you will start getting an error. When we went for Peclet number equal 5, you realize there's a change in the flow direction of the solution, and this is exactly what you see in here, right? And that's why you see the approximation here is not matching well. Okay, so what we are trying to do is to improve the numerical scheme to catch that profile here. Okay, so for small Peclet number, again, let's write down that for small cell Peclet number, analytical solution is linear. Right? So assuming any scheme that assume linear variation of phi over the cell should match the behavior of the analytical solution. That's why the central differencing scheme was working great at small number of Peclet number, because the central differencing scheme is assuming linear change inside the cell of the phi value, which is matching what the analytical solution should be. The more you go away with your value of Peclet number, you move away from 0, right? You will start getting a little bit of an error, okay? I'm trying to recap what was a Peclet number for the low velocity example. Let me see. I think I can go back to my sheet here. That should be in the previous one. I think that's rho UA. Let me calculate actually the Peclet number for the low velocity here. So we had rho. Where's my piece of information here? Okay, so that's rho U delta over kappa. If I recall correctly, rho is 1 and U was 0.1 and delta was 0.2 and kappa was 0.1. So Peclet number was actually 0.2. So in this one here, when we use a central, Peclet number was actually 0.2. The exact value is 0.2. Yep. So you see that at very low Peclet number, the approximation, the solution is matching nicely because central differencing scheme assuming linear variation, and also the exact solution seems to be linear in that part. It's not perfectly linear because we know that linear is only at Peclet is equal 0. So I would say if you want to see the linear, I should see something like this. This is for Peclet equal 0, right? And because I moved a little bit from 0, I started getting that curvature of the exact solution, but still, central differencing scheme was doing great job. It's catching nicely the exact solution. But when we went to the Peclet number of 5, now the approximation was totally wrong for central differencing scheme. That's why we moved to the Upwind one. So let's go back to the distribution or the classification of the solution here. So for a small Peclet number, solution is linear. That's the exact solution. I'm talking about the exact solution. You can see here. And the scheme that assume linear variation of the phi over the cell should match the behavior of the analytical solution. That's why the central differencing scheme was perfectly working and matching exactly the analytical solution here. For large value of Peclet number, let's assume that we're looking for large, something greater than 1. So let's Peclet is much more than 1. Look at this graph here. This is the exact solution of phi, right? What is the slope of that line? I'm drawing a tangent to the solution, to the analytical solution. It's almost horizontal, right? So the slope equal 0. So d phi by dx is equal 0. Means that phi is constant, right? Then you will start changing the slope here and changing the slope here, right? But up to this level, your slope is equal 0, your phi is constant, and this is what we assumed in the Upwind scheme. So the Upwind scheme worked very fine up to this level here. As you can see, as long as the slope of the line is horizontal, we were so close from the analytical solution. When the slope started to change, assuming constant property is not going to work, and that's why the Upwind scheme failed in this region here. So the Upwind scheme worked nicely as long as the slope is equal to 0, which is the early stage of the solution for higher Peclet number. In the example, Peclet number was 5. That's a high Peclet number. So they're assuming that the Upwind scheme, which assumed that the property is constant over the cell, phi is constant, it's actually showing very good contribution up to the level when the slope of the solution starts to change. You maybe are getting a little bit of an error, even with the horizontal slope, right? It's not really overlapping exactly. And this error because we are getting the value from a single data point, not from 2 points. So the accuracy is less. But still, the behavior could be, if I fit these data points, I may get a linear solution here, which is close to this one, which is showing the difference between the tangent and the right one. As soon as the exact solution is deviating in a slope, now you cannot assume the property is constant. I can no longer assume that. There is actually another Upwind scheme called linear Upwind scheme. So the people actually doing linear distribution here, but I don't want to get into this. It's a little bit confusing. So let's stick to this and see how we can improve the accuracy of the Upwind scheme. So when the real solution is changing the slope, it's actually matching nicely with what we have without adding a new scheme. Okay, so again, what's happening here? This is high Peclet number. What does that mean? The convection contribution is very high compared to the diffusion term. So some group or some scientists came with something called the hybrid Upwind scheme. So let me write down here first the notes so you don't forget that. For a large Peclet number, the slope of analytical solution approximately equals 0, which means that phi is equal constant is a good approximation up to the slope changing away from 0. And that's explained why the Upwind scheme, which always assume phi is constant inside the cell, was working fine until the actual solution is changing or moving away. The slope is moving away from 0, and that's why we got that failure in the last couple of data points. So how to fix that? Fixing that was made by the hybrid Upwind scheme. So let me write down so we are covering now the hybrid Upwind scheme. I'm going to list what are the characteristics of the scheme, and then I will go into example. Then I will talk about how to compare the three of them together between the central differencing scheme, advantage, disadvantage, and the Upwind scheme, advantage, disadvantage. Then talk about the hybrid Upwind scheme. In the hybrid Upwind scheme, it's indicating the following. Number one, if your Peclet number absolute value is less than or equal to, use the central differencing scheme. If your Peclet number absolute is greater than, actually the equality is not here, the equality is here, use the Upwind scheme. Plus, since you are going into high Peclet number, the convection will be more dominant. You can neglect the diffusion term. One additional note that sometimes is not mentioned clearly, you look to the neglecting the diffusion for the interiors. Notes. But the nodes that's close to the boundaries, the impact of the boundary condition has to be considered. So we're going to look into example here. So this is simply the hybrid Upwind scheme. Okay, so if you are using the Upwind scheme, if you are still using the normal Upwind scheme, which is assuming phi is equal constant, the additional thing that we're adding here is we're going to neglect the diffusion term. When you do that, we believe that error that we are getting in that graph for the last two data points is coming because of the presence of the diffusion, and the Upwind scheme is not made for diffusion, it's made for convection. So if we eliminate the diffusion, we may end up pushing this point here, pushing this point here. So we will figure out that by solving an example here and see how the results would looks like. So let's go back to the example. I'm going to go back to phi is equal 1, phi A, phi B is equal 0. The total length is equal 1 meter. Rho is equal 1 kilogram per meter cubed. Kappa is equal 0.1 kilogram per meter second, right? And A is equal 1 meter squared. And we're going to divide that into 5 cells. I have a velocity U that's equal to 2.5 meter per second. And we would like to calculate the value of phi 1, 2, 3, 4, and 5. Okay. We did the first trial using central differencing scheme. We got that diversion solution. That was our first trial. Then we did apply the Upwind scheme using 5 cells. The solution for this, we went from 5 cells to 20 cells to drop down the Peclet number less than 2, and it works. But it costs you more work. Instead of working with 5 cells, we had to work with 20 cells. The second short solution is to stick to the 5 cells, but use the Upwind scheme, which assuming the convection is, the approximation of the convection term is constant value of the function phi inside the cell. We did, it's improved. Instead of having that diversion, we got conversion solution, but we got some error when the slope of the analytical solution was changing itself away from zero slope. Now we are trying to fix that part by applying the hybrid wind scheme. The only additions that we got with this new scheme is actually to neglect that diffusion term. So let's see how we're going to deal with that. I'm going to start again with, as usual, the interior nodes 2, 3, and 4. We all know that the equation end up to be FE phi E minus F west phi west is equal to kappa east A east d phi by dx the east minus kappa west A west d phi by dx on the west. This is after you write down the general transport equation, you take the divergence, you integrate over the controlled volume, you apply the divergence theorem, then you end up having this equation here. Now, what's my Peclet number? Peclet number is equal 5, right? If you do the F, rho UA, if you do the D, which is kappa A over delta, delta is 0.2, you will end up having Peclet is equal 5. Let's calculate this actually here. So I will calculate F is equal 1 times 2.5 times A, which is 1, is going to be 2.5, and D is going to be 0.1 times 1 divided by 0.2, so it's going to be 0.5. And now if I calculate Peclet number, it's F over D is going to be 2.5 over 0.5. I'm going to get 5. Just to remind you what are the values. Okay, now Peclet number is greater than 2, so I'm going to stick to this. Use the Upwind scheme for the convection term and neglect the diffusion. Okay, let's see what we're going to do. Since I'm talking about interior nodes, I'm going to, these are interior nodes, right? I'm going to neglect the diffusion for the interior nodes, which means that this is going to be 0, this is going to be 0. What we're going to end up having, we will have if E phi E minus F west phi west equals 0. Now, this is the cell phase. Now, according to the Upwind scheme, right? If I'm picking this point here, this is the east face. This is phi east. It's going to be the phi P, if that's my P point, right? And the west one will be the west face. So phi E was equal to phi P, and phi west is equal phi of the capital W. This is for positive flow, which is true because I'm going this direction here. So this equation will be simply Fe phi P minus F west phi west equal 0. I will bring that to the other side. So I have F east phi P minus F west equal to F west phi west. This is my A west plus 0 phi east, right, plus 0 SU. So that's my A east. That's my SU is 0, right? Then for this term, I will add F west minus F west. So now I will have this is A west, and this will be the minus SP, and I know that for mass conservation, F east and F west will be the same, so this will actually will cancel out. But let's list the coefficient here. So I will have AP phi P equal A west phi west plus 0 phi east plus 0. If you want to just write up to here, that's fine too. What is your A east? A east is equal 0. What's my A west? A west is equal F west. And we know that F west is the same as F east as F. That's going to be 2.5. What about the SU is 0. What about the SP? SP is going to be minus F east minus F west, which is going to be 0. What is my AP? AP is going to be the summation of all of that. This is 0, so it's going to be as F west, which is equal F, which is equal to 0.5. These are the coefficients for the interior nodes. Okay, You realize that? This is the extra step that we took here by eliminating this is equal 0, because this is the diffusion for the interior nodes. Okay? Now, let's go back for node number 1. I will go for node number 1. That's the first node. Let me draw the so that's node 1. That's node 2. This is my P. This is my east. This is my east face. And this is my west face. And I remember that phi A at that boundary is equal 1, right? And the flow is going into that direction. Okay? Again, my Peclet number is 5. That's number 2, node number 1. For the, this is phi east. This is phi P. That's for the Upwind scheme. So, what's the governing equation? The governing equation is F east, phi east, minus F west, phi west, equal kappa east, A east, d phi by dx on the east, minus kappa west, A west, d phi by dx on the west. Bear with me. This is very important here. So, for the convection term, I'm going to use the upwind according to the positive flow here. Phi east should be the same as phi P, and phi west is the same as phi A, which is equal 1. Okay. Now, from the east side, I'm getting convection from interior node, so this will be 0. That's the assumption of the hybrid upwind scheme. But the diffusion near the wall, I cannot ignore that. So what's gonna looks like here, this equation is gonna look like this. What is d phi by dx on the west face will be phi P, right? I go back to the linear, right? This is P, this is the phi A, this is phi P, right? I don't care about the diffusion into the interior node, so I will be phi P minus phi A divided by the distance here is delta X node. So now I don't need that anymore. I can go and write down the full equation. I have F east phi P minus F west phi A equal to, this is gone, there is minus, I will have, I will call that kappa A, AA, just to stick to the face A here, divided by delta X node, multiplied by phi P minus phi A. Now I'm going to collect the terms. I will have FE plus kappa A, AA, it's neither east or west, divided by delta X node. This is totally multiplied by phi P. It's equal to, what else we have? 0 phi east, because we ignore the diffusion here, right? And I don't have a cell in the west, so I will have 0 phi west, but I will have this FW plus kappa A, AA over delta X node. This is totally multiplied by phi A. This is my A east. This is my A west. This is totally my SU, right? I have A east is 0, A west is 0. So this is totally here is my minus SP, which is the same as AP, right? So this is going to be AP phi P equal to 0 phi east plus 0 phi west plus SU. This is the governing equation, where A east is equal 0, A west is equal 0, SU is equal F plus, again, F east equal F west equal F, and D east equal D west equal D. Just for simplicity here. What is this? I know that D is equal kappa A over delta X east or west, right? Either one, but this is half the distance, so which means that numerically, this is 2D. right? So that's 2D. I don't write it down here D, so I don't make any confusion. But when it comes to numbers, I will write it down. F is, as a value, is 2.5, and D is equal 0.5. So 0.5 times 2 plus 2.5, I got 3.5. Then I have SP is equal minus F plus 2D. F, and this in numerical value is 2D. This will be minus 3.5. Then if I want to do the AP, AB is going to be F plus 2D. So it's going to be actually 3.5. So these are the coefficient for node number 1. Now, next, we should go and do node number 5. So what is new here? This is the new thing. We ignore the diffusion term that's coming from here. Okay, now, node number 5, the last node. Here's the domain. This is boundary phi p, which is equal 0. Then I have, this is node 5. This is node 4. I'm going to call that P. I'm going to call that west. There is the west face. And the east face is overlapping the face B. So that's the east face. Now the flow is coming this way, right? So for the upwind scheme, this phi west is coming from phi capital W. The flow is coming this way, right? And this is the east. So phi east is from the upwind node or upstream node, which is phi P. So again, that's node number 5. Step number 3, the equation is F east phi east minus F west phi west is equal to kappa east A east d phi by dx on the east face minus kappa west A west d phi by dx on the west face. Okay, so what is phi east? Phi east, according to the upwind scheme, is phi p. What is phi west? Phi face west is the same as phi node west, right? What is, there's diffusion happening here. It's interior diffusion. So what's happening diffusion in the west side is neglected. So that's actually 0, according to the hybrid scheme. So this will d phi by dx. Again, I will go back to the linear change, right? So we have a linear change here. This is phi p, and this is phi b. So if I want to get d phi by dx on the east face, will be, actually we do the opposite, right? So we go from this side to this side here, of this one. So it's going to be phi b minus phi p. So this will be phi b minus phi p divided by the distance here, which is delta x node. I'm going fast because we already covered that many times in a lot of examples. Go back to the recordings before, you will see a lot of examples covering this. So now what's going to be the equation is going to be F east phi p minus F west phi west equal to kappa east A east over delta x node. I'm going to call that phi b, like what we did. So that's the face B, that's my east, just to exclude values from east and west, so to avoid any confusion. And this will give me phi b minus phi p. Okay, now we need to collect the term. I will have the following. I will have Fe plus kappa of face B AB divided by delta x node multiplied by phi p equal to F west phi west plus kappa B AB divided by delta x node phi B. I will add also 0 phi east. So this is my A east. This is my A west. This is my SU. Now, looking into here, I don't have A west here. So I'm going to add, I will subtract F west, and I will add F west. So this term here will be F west plus kappa B AB divided by delta x node plus F east minus F west That's going to be this term here. So this is A West, like this. And I know this will be 0, but in total, this should be minus SP, and this combined term here should be the AP. So I will end up having AP phi P equal A East phi East, sorry, A East is 0, phi East plus A West phi West plus SU. Let's list the coefficient here. A East is equal 0. A West is equal F West, which is equal F, which is equal 2.5. SU is equal to kappa A over delta X node. That's a value of D2D phi B. Even I know that phi B has a value of 0, so this will be actually 0. Then what's my SP? SP is negative. This is 0, and this will be 2D, so it's going to be minus 2D. And the AP will be simply F plus 2D. As a value, this will be minus 1, and as a value here, this will be 3.5. So these are the governing equation using the hybrid upwind schemes. The only new stuff here, this is the neglected diffusion, neglected. That's the new thing here. So now let's collect these coefficients in our table of coefficients and see how things will change. See how the numerical solution looks like when we compare it to the analytical solution. Will that improve the deviation between the last 2 points when the analytical solution actually changed direction? So I'm going to build up the coefficient table. I'm going to start by A West, A East, SP, SU, and AP. That's node 1, node 2, node 3, node 4, and node 5. Let's go back to the nodes here with node number 1. For node number 1, these are the values. So I got A West is equal 0, A East is equal 0, SB is equal minus F plus 2D, and SU is F plus 2D, and AB is F plus 2D. Okay? This is just one thing to be sure of. Yeah, so for the SU, it's F plus 2D times phi A, which is 1, by the way. I'm just putting everything in a full format here. Okay? That's the coefficient for node number 1. Let's go for the interior nodes. These are the coefficients. So I got A West is F. I got A East is 0. I got SP is 0. You want to write it down, F East minus F West, or F minus F is going to be 0. SU is already 0, and AP is F. Now I will repeat that for node 3 and node 4. Now for node number 5, I got the coefficient here. I got A West is F. I got A East is 0. I got SP is minus 2D. I got SU is 2D phi B. And I got AP to be F plus 2D. I can substitute numerically here, so that's 0, 0. That's minus 3.5. That's 3.5 because phi A is 1, and this is also 3.5. It's 3.5. I'm just doubling checking my numbers again to be sure that I'm doing the right things here. Yep, that's correct. Then going to the next one, if is 2.5, 0, 0, 0, 2.5, 2.5, 0, 0, 0, 2.5, 2.5, 0, 0, 0, 2.5, 2.5, 0, minus 1. This is 0, and this is 3.5. So these are the values. If I want to construct my matrix, one, 2, 3, 4, and 5 is 1, 2, 3, 4, and 5. Diagonal values is my AP's values. So for node number 1, I will have 3.5. I will have 2.5. I will have 2.5. Have 2.5, and I will have 3.5. Now for node number 1, 0 east, 0 west, right? I have nothing in both directions. So I will have 0 east and nothing in the west. Then I'm going to fill the rest by zeros. Node number 2, the east is 0. The west is 2.5, and we know that we have to add the negative value, 2.5. Then the rest are zeros. For the next one, you just repeat the second line. Then you repeat the third line. Coming for node number 5, I have the east is 0, but I have the west is minus 2.5, 0, 0, 0. So let me write that in a clean way. So I have the coefficient matrix looks like this: 3.5, 0, 0, 0, 0. Then I have minus 2.5, 2.5, 0, 0, 0. And I have 0, minus 2.5, 2.5, 0, 0, 0, 0, minus 2.5, 2.5, 0, 0, 0, 0, minus 2.5, and 3.5. Now, before we proceed, we're going to look into the Scarborough criteria. You remember Scarborough criteria? This is the AP's values. This is AP. These are the east and west coefficients. So I will take the absolute value for all the neighbor coefficient. It's actually 0. So 0 over 3.5. That's 0. That's less than 1. Nothing wrong with that. Here I will have 2.5 divided by 2.5. That's equal 1. Here I will have 2.5 divided by 2.5 equal 1. I will have 2.5 divided by 2.5. You sum all the east and west. You take the absolute value, then you divide by the absolute value of this. Is going to be 1. Here I will have 2.5 divided by 3.5, which is 1. Less than 1. So Scarborough criteria said the summation of the absolute of the neighbor cells divided by the absolute value of AP has to be less than or equal 1, with at least one node less than 1, or at least one node. I have actually 2 nodes less than 1, and the equalities exist. So Scarborough criteria is a checkbox. Now I can solve analytically, or you want to solve numerically, that's fine. So you're going to have here phi 1, phi 2, phi 3, phi 4, and phi 5. And now you need the free terms on the right-hand side. What they're supposed to be? It says U value. So I should have 3.5, 0, 0, 0, 0, 0, 0, 0, 0. Then you solve that numerically, so you can easily get the values of phi. What we got for phi, I got phi 1 is equal to 1. Phi 2 is equal 1. Phi 3 is equal 1. Phi 4 is equal 1. And phi 5 is equal to 0.7143. Okay. If we compare that to, this is the hybrid, if I compare that to the value of phi1, phi2, phi3, phi4, that's a hybrid upwind. And these are the values we got for the upwind. What were the values? 0.9998, 0.9987, 0.9921, 0.9524, and 0.7143. These are the values. So what happened? We got a little bit of improvement in the solution, and it seems to be it's more accurate. Let me look to the chart so we can actually show you the plotting. By the way, sometimes you call the hybrid differencing scheme, because we use the central differencing and the upwind differencing as well. So I like to call it hybrid upwind, but you can call it hybrid differencing scheme as well. So this is a graph showing actually here, these black dots here is showing the solution. We got improvement in one point, but we still have a little bit of division, but we are much better compared to this, right? So this point actually jumped up here, but this point still almost at the same location. So we still have a little bit here. So we got a little bit of improvement when we ignored that diffusion term, but still it's not sufficient to match exactly using 5 cells. If you use 25 cells like this solution here, you see that open squares, they are matching fine, okay? But with using a small number of cells, again, using 25 cells mean that you are dropping down your Peclet number. So it's no longer 5, which is going to work fine. But again, if you want to use a small number of cells like 5, the hybrid differencing scheme improved partially, but not perfectly. So this means that we need to look into other type of schemes to be sure that we can get the exact solution matching with very minimal error with a small number of cells. So you don't have to be computationally expensive, having large number of cells to do the calculation. And that's what we're going to look into it in the next recording.